All right, so now I'm going to take a minute to solve a couple of exponential and logarithmic equations to show you how it's done and to dispel some of the fear of handling these. So to do this, I'm going to start with exponential equations, and we're going to work with, let's see here, page 383. That's not right. Page 380. And we're going to do number 16 and number 18. So problem 16 is about the world population, and it says the population of the world was approximately 7.1 billion in 2013. The observed relative growth rate was 1.1% per year. We're going to estimate how long it would take this population to double, and then estimate how long it would take the same population to triple. So, the interesting thing here is that we don't actually need to know the population for this to work. So we have what we're given. We're going to be using the exponential growth formula. I'm going to modify it slightly. So we're going to use the population as a function of time equals the initial population times e, the rate, times the time. We are given E0 equals 7.1 billion. We are given R is 1.1%. And we're asked to find how long it takes to double. Now, double means we want P of t equal to the initial. And because this is going to be in terms of this given, we don't need to worry about what P of 0 actually is. So I say 2 P0 equals P0 E. R is 1.1, which means it's 1. Move the decimal point, 0, 1, 1. D. Simple algebra tells me that doesn't matter. On both sides, I can factor it out. And then I'm left with 2 equals e to the 0.011 t. Here we use the nature of the exponential equation, and we remember that since we're solving for t is in the power, it's in the exponent of this equation, we have to do something that gets it out of the exponent. Here, we used algebra to divide out something that had been multiplied. So division and multiplication are reciprocal functions. So in this case, we need to use the reciprocal function of the exponential, which is the logarithm. In the case of e, is the natural logarithm. We take the natural logarithm of both sides of this equation. We end up with ln 2 equals ln of e to the 0.011t. And we say it's ln 2. Use the properties of this being reciprocal. That is to say, the natural logarithm of e to any power is the power. So the natural logarithm is what cancels the e. And then we just solve for t here. We end up with natural logarithm of 2 divided by 0.11 equals t. Now, if we then plug that into our calculator, what we get is t equals, and the number in the calculator will look something like this. And this is in years. And if you write it this way, you are mathematically correct. But all of this is nonsense. This is worthless crap. 0.01338 years is what, 3 days? I asked you how long it will take the population to double at an approximate rate of 1.1%. And you tell me it will take 63 years and 3 days. You are being way more accurate than you have any business being. You need to round this number the accuracy of the information you have. 63 has 2 digits because 1.1% and 7.1 billion have 2 digits. If you've taken chemistry, you've gone on a long description, probably a class or two worth, of significant figures. That is to say, on a chemistry test, even on a physics test, if you were to write this sort of thing down, it would be wrong. This answer is not correct. This assumes far more accuracy than you have, and accuracy is important in dealing with these things. In physics and math, a lot of the time you just round how many figures you have. In chemistry, you have to follow the significant figure rule more carefully because you're dealing with small amounts of chemicals, and the precise differences can be very important. Or in this case, it's safe to round to, say one more decimal place than you have if needed, or however many digits you have. 63 years versus 63.01. 1/100th of a year is 3 days. We don't care about that. Now, I can use the same process. So that said, the answer to this question is 63 years. I can do the exact same process, find the tripling rate. So this is how long it takes the population to double. If I want the population to triple, all I do I solve this problem the same way. You can see that this ends up being ln 3.011, which in this case is 99.87384 years. .87. If I round it to here, that's still a lot. If I round it to 99.9, I get 99.9, but I should round that to 100. So this is really 100 years. All right. So, short explanation of what happened here. You can prove to yourself that the step I skipped, but I skipped this one, and this one, obviously isn't going to be that much of a big deal. The only thing that changes from finding a doubling to a tripling is what P of t originally, you want P of t to equal. I wanted it to be 2 times the principal initial population. I changed nothing about the initial population. I changed nothing about e to the 0.011, and t is what we're looking for. So the only thing I changed was I made this 2 a 3. So I can just go here, put a 3 in instead of a 2, and solve this problem. Now, when I say solve this problem, I mean solve it with a calculator. So here's one that I have. This is a TI-86. And you can see in this area, I have a natural logarithm button. I have a log button with a common logarithm. Both of those have a reciprocal. So if I hit second on the natural log, I get e to the x. If I hit second on log, I get 10 to the x. And an issue that I've seen before that I've been asked about is how do you get scientific notation on some of these calculators? And see this button that says EE? Use that. When you press this EE button, and it's either going to be 2 capital E's or maybe even just 1 capital E. Let's see if you can see it here. If I write 5, hit that EE button, it shows 1 E there, and we're at -5. That E means 10 to that power. So you may need that, especially in the next section when we talk about briefly logarithms. Now, I'm going to take, this was problem 16. I'm now going to do problem 18, which is exponential decay, and show you how they're very similar. So I'm going to erase this and start problem 18, also on page 380. And problem 18 looks like this. It talks about radioactive cesium. So we learned that cesium-137 has half-life, which is given the Greek letter lambda, equal to 30 years, I believe. 30 years. And we say we have a 10-gram sample of this. And we're asked 4 different things here. We want to find a function, m of t. We're asked A, find mass as a function of time, equals mass initial, using binary, 2 to the minus t over h. That measures the mass after t years. And And B, do this with an exponential. And C, we want to, what is m of t, or specifically, I can write it a little bit easier. I can say find m of 80. And then D, when does m of t equal 2? So we're being asked to do a lot here. So we'll start at the beginning with A. I'll say, what can I do? What is this really asking me? Well, this is actually pretty simple because most of this is given. So for A, I want m of t, and I just plug in the numbers here. I get 10 times 2 to the minus t over 30. And that's a solvable problem. I just need to solve that for t in order to determine what the time would take, right? Which for numbers for section C here is not going to be difficult. I just need to plug in 80 and I'll have that answer. And then B is a little bit more complicated. He wants me to take this and find it in terms of this. So what I need to do first is find out how to relate R to H. Now, there's a simple way to do this, and if you look on page 375, you can follow along. But what I say is I let m of t be half of m of 0. So I say I want to find this when m of t, the initial over 2, right? To find the half-life, I need to know when there's half of it left. And I know the half-life. That equals e to the minus rt. So I'm going to solve this equation to get something useful. And I'm going to do what I did before. I'm going to say, well, oops, sorry, I wrote it down wrong. I want m0 equal 1/2. Sorry about that. I want that to happen. I want 1/2 equal e to the minus r. Which means I need to take a natural logarithm, like I did in the last problem. So I need natural logarithm of 1/2 equals minus rt. And now I need to solve for r. Right. So what is r? What is t in this case, by the way? If I'm talking about the half-life. I know the half-life is said to be 30 years. So we can also say that this is this h half-life instead of this lambda. I want to use both because you'll see it as both. So this is really, half-life is 30 years. If I'm getting it half, then this t to be 30 years. So now I just solve for r. I have the natural logarithm of 1/2 over 30 equals r. And if I plug that in, I get 0.02. So to use this as an exponential, this is my rate. So I'm going to rewrite these things over here to include these so that I can solve this problem by doing part C. So I have, and I will use blue to show everything I've plugged in. Okay. So let's solve part C. And I want to solve part C using both of these equations. So part C is, what is m of 80? So I write m of 80 equals 10 times 2 to the minus 80 over 30. All right, well, that's simple. I just plug those numbers in. And I get 1.57 grams remaining. So I started with 10, and with a half-life of 30 years. After 80 years, I have 1.57. Now if I say m of 80 equals 10 e to the minus 0.023 times 80. So here I had 2 to the power of negative 8 over 3. Here I have e to the power of minus 0.023 times 80. And both of those multiplied by 10. And here I get 1.59. So those are both 1.6 if I round them. So that's good. There's a difference of approximately 1.26. So there's a 1.26% difference in these answers. And that is simply due to the fact that this is more accurate than this because of what we discussed when dealing with exponential growths and decays. This is the continuous amount, and this is periodic. So both of these answers are right depending on the equation you learned, and no matter which one you use, both of them give you a fairly accurate answer. So whichever one you're asked to use that one. Or you may be asked to use both and talk about what the difference is. Now, I introduced a concept here. What is the percent difference? This equals your answer minus expected answer divided by the expected answer. Usually take e to be the expected. So in this case, I took 1.57 minus 1.59. It's the absolute value of this because I don't care whether it's positive or negative. Divided by 1.59. And that gives me that 0.0126. Okay, so we have our value. And now I can say, well, when is there only 2 grams left? How do we solve this one? So this is part C. Now I'm going to do part D. I'm going to solve it using this one first. I'm going to say, when does 2 equal 10 e to the minus 0.023 t? Right, because now I'm trying to find t. So like in the problem before, I'm going to solve for t, which is in the exponent. Well, the first thing I can do is I can move this 10 and get 2 over 10, which is 1 over 5, equals e to the minus 0.023 t. I can take the natural logarithm of both sides. For natural logarithm of 1 over 5. Now, that equals minus 0.023 t. So I have the natural logarithm of 1 over 5 divided by 0.023 minus 0.02. 0.023 equals t. And here we find the properties of any logarithm under that's less than 1. Logarithm values less than 1 are negative. When you plug this value into your calculator, you'll get a negative number, which is good because we're dividing by a negative number. So this number better be negative so that when we divide by this, we get a positive time because we know full well time only goes forward. And when you do that, you get t equals 69.97 years, 69.97, which we round to 70. Right, because we're talking about 0.03 300ths of a year is about 9 days. Don't care about 9 days out of 365. So here we are. That's 70 years. If we do the same thing using this other equation, we'll get basically the same answer. I'll leave that as an exercise for yourself to see how well you do. The last thing I want to do is logarithm problem. So same basic thing, but in reverse. Instead of taking the logarithm both sides, I'm going to raise something to an exponent. And just to show that it's different, I'm going to use the common logarithm instead of the natural logarithm. So here I move on to, I believe this is page 186. Yes, page 186. And we're going to compare decibel levels. So decibels are one of the logarithmic scales we mentioned. And it has this form. And the reason we call it decibels is because we have this 10 times log here. If you move this 10 over, you have d over 10. D. So decibels, 1/10. And what's happening here is we're having these I's intensity. This is initial intensity, or reference intensity. And I sub 0, I naught, is the reference intensity of 10 to the minus 12. And this is in watts per square meter if we're dealing with the physics of it. So it's the amount of energy per square meter at a certain distance from a certain sound at a certain frequency. But the point is, it's this much power watt over an area. And we're going to be asked to compare the intensity I of 106 decibels versus 120 decibels. So in order to do that, we have to solve each of these things for I. Now, the way the decibel scale works is every time you go up 10, you have 100 times perceived effect. So to do this, if I have to solve versus 106 and 120, let's solve 106 and 120. And by that, I say for E equals 106, this is 106 equals 10 log I over this, the initial reference log. So let's do some math here. I'm going to say I can divide both sides by 10, 106 over 10. And I will use the law of logarithms to say that log I minus log I naught. Let's say if you divide the logs, you're subtracting them according to the law of logarithms. And now I can move this to the other side. I add this. This is a number, right? This is 10.6. This is the log of 10 minus 12. This is log I. Well, this is another law of logarithms issue where I'm going to use the fact that log of a to the c equals c log a. I'm going to say this is 10.6 plus minus 12 log 10. Now this is the common log of 10. So in the same way that if this was the natural log of e, it would equal 1. The common log of 10 equals 1. So that's 1. I have 10.6 minus 12 equals log I. So I have 1.4 negative equals log I, which means I equals 10 to the minus 1.4. this is the definition of the common logarithm, right? This answer is the power that 10 is raised to give you I. So I is 10 to the 1/4. And then I can do the same problem with 120. Right? So I divide by 10, end up with 12. Equals, separate the logarithms. Move this over to here. Now I remember this is 12 minus, so now plus, log I0 equals log I. Log of I0 is minus 12. So 0 equals the common log of I. Now remember, this does not mean I is 0. This means I is 10 to the power of 0. Which on its own is 1. And the last thing, so now I have this intensity is 1. This intensity is 10 to the power of minus 1.4. And now I want to get the ratio of the intensity of rock music at 120 decibels to that of a power mower at 106. So the ratio, I want I of 120 divided by I of 106, right, which equals 10 to the minus 1.4 divided by 1, all the way around. Put that into your calculator, and you get 1.38. So the intensity, the amount of power per square meter you experience at 120 decibels is 1.38 times that of what you experience from 106 decibels. So that's going to be it for today. This logarithm problem, those exponential ones. If you have a question, ask sooner rather than later. And I will see you in class next week.